Now we will continue on the chapter 7, satellite image understanding and interpretation. The first, we will look into the thermal infrared. Okay. As we learn or we study in the previous chapter, we talk about the spectral properties, we talk about the satellites and so on, and we also talk about the multispectral, those RGB bands that represents the natural world and so on, and the other properties that also available in the satellite images are thermal infrared. And as we see, all objects within the Earth's surface, they do emit those EMR or electromagnetic radiation, and this energy basically is emitted in thermal infrareds. There are some part of the energy that produce heat, and this heat, they have the properties of the thermal infrared wavelengths, which is from the 3 until 14 micrometer. This energy able to be detected by the remote sensings in basically when the energy is big enough to be detected. And what are the ultimate source basically is due to the shortwave solar EMR. So basically the energy that comes from the sun, certain properties on the earth able to absorb the energy, okay, such as concrete surfaces, tarmac, buildings, and many more. And the landscape will absorb the shortwave visible and the near infrared radiations. After certain specific energy has been absorbed, then the energy will be re-emitted back, okay, in the longer thermal infrared wavelengths. And these longer thermal infrared wavelengths basically is the one that being recorded by the remote sensing sensors. Okay. Apart from that as well, our Earth also produce their own energy, their own thermal energy, such as the geothermal energy, or it could be the human-made thermal energy such as fires. Okay, and now we look into the elements of the radiated energy, radiated energy here. Sun basically they have the highest temperature, which is 6000 Kelvin, and the lambda maximum is 0.48 micrometer. Okay, and the Earth basically they produce about 300 Kelvin, which is about 30 something Celsius. Okay, with the lambda maximum 9.67, and even the liquid as well, they do have their own energy being produced, and this energy based on the wavelength able to be detected by the remote sensing as it radiates the energy. Okay, and basically in this, okay, by using the Stephen-Boltzmann law and Wien's displacement law, it is enabled to capture the thermal infrared wavelengths and thus calculate the EMR that being radiated. Okay, and here this is what we call as the atmospheric window, and this atmospheric window basically explains about the rate of absorption by the atmosphere towards certain specific wavelength. As you see here, from 0.1 until 0.3 micrometer, oxygen absorbs most of the wavelength. And now we look into the thermal infrared here. So when you look into the thermal infrared, which is around here, from 3 until 14 micrometer, most of the elements that absorb this thermal energy consist of three things, which is carbon dioxide, water vapor, and ozone layer. So the idea is, why is knowing the atmospheric windows for thermal infrared energy is very important? It is because that from here we can try to understand. Okay? We are trying to understand with this window, with this atmospheric window, those three elements. If those elements have the higher occurrences, or higher presentations in the atmosphere, it will absorb, the red absorption will be greater. Therefore, let's say, taking the example 3 until 5 micrometer, if one area they have more carbon dioxide density, so the red absorption will be greater. Thus, it explains why the temperature is higher, and also we can relate it with the greenhouse effect. The interpretation of the thermal energy requires the thermal thought, such as the thermal atmospheric path are different and the radiations are no longer reflected. So thermal infrared is used to identify the Earth's surface based on the thermal properties, evaluate significant changes in the thermal characteristics of the surface over time. So when we talk about environment monitoring, we look into those two things, which is we like to identify kind of the features on the Earth's surfaces based on the thermal properties, and this will brings into the elements of the features, the elements or the what constructs the features on the Earth. Number 2 will be to evaluate the significant changes. So meaning to say, over the time, when the surfaces change, such as land use has been changed from the agriculture area into the urban areas, therefore the thermal characteristics will be changed as well. It is due to the representation or the constructions of the buildings, which contributes to the different or the significance of the difference of the thermal energy. And this interpretation of the thermal infrared imagery will usually interpreted qualitatively due to the difficulties to extract the actual or the exact temperature of the surface. However, it is qualitatively known that it shows the warmer and colder areas. Okay, and other restrictions are time constraint, which is day of the image will be collected, and the relationship with the solar radiation on that particular time, as well as cloud and also the humidity of the areas on that particular time. So the remote sensing instruments measures the radiant temperature as opposed to kinetic temperature. So basically, when we talk about the radiant temperature, it is relates on the radiant temperatures, that being which is the temperatures are basically the energies that radiated from the surfaces over the atmosphere, as opposed to direct measurement of the surface itself. So what is basically the kinetic versus radiant? So kinetic temperature is what's called as a true or real temperature, where the energy of particles in random motion, where molecules collisions transfer energy. Therefore, they must have a contact through the object. Usually, is a thermometer. You can measure it by a physical contact of the thermometer and so on. However, for the radiant temperature, it is different because it was external. Okay, it was external, and molecules collision cause a change of energy states with result of the EMR, that means radiated from the surface, and this EMR that radiated called radiant flux. Therefore, the amount of radiant flux is called radiant temperature. Okay. Now we are looking into the Landsat data of Lambda 5 shows you the temperature of the area. The brighter the area, the higher the temperature, while the colder the area, the darker the images. As you compare here, why does it happen? Usually most of the areas we shown in the band 2, 3, 4, where these combinations of bands are sensitive towards the physical features that have the human-made buildings or features. Observe here where most of the areas that have the brightest color shows the areas that have zero water, meaning to say the area, the materials that are being used to construct the features are something like concrete. They doesn't absorb water, and thus shows here that those features also have the higher energy as opposed to other areas which is mostly vegetated areas and water, of course. The second one, we look into radar. So radar basically, as we discussed in the earlier chapter, it is a active sensor devices. It produces their own energy. It's good to use because it able to penetrate the cloud, make it all weather system, and it is based on the user specific time. Okay, and it able to sense the wavelength outside the visible infrared of the spectrums, where it give more additional features of the Earth surface. Okay, and it able to penetrate certain degree of the features such as vegetation, sands, and more. It have its own source of illuminations. Okay, and one thing is they are able, due to the data of the radar being captured through oblique point of view or side of view, as opposed to normal remote sensing, which is vertical. Therefore, it able to measures the ocean and lake wave properties. Okay, but the idea of interpreting the radar is totally different from the normal multispectral data from the normal remote sensings. Okay, so it requires an understanding of how the EMR is sent, received, and recorded by radar systems, and as well how microwave energy interacts with the Earth's surface. So the idea is like this. As I said before, the radar systems, they must face obliquely towards the features, the target that you want to capture. So the pulse of EMR at a specific wavelength is sent to the transmitter. Okay, so when in sending mode, the duplex sends the pulse of the energy through the antenna towards the Earth's surface in certain specific degree, and the duplexer switch to receive mode. Here, the backscattered energy is sent to receiver and recorded. So there are some pulses, higher energy being sent, and slightly lower energy will be absorbed, will be reflected by the surface and be detected by the sensor. So the pulse of the EMR sent through the antenna also has a specific duration, such as the pulse length, and it was measured in the microsecond. So these are the bands that being used by radar, from Ka band until P band. Okay, so the common lambda is in cm. Okay, and these are the range that the sensors able to detect, and these are the velocity or the velocity or the frequency of the wavelength we serve. Okay, for the polarizations, for every radar they have their own polarizations. Okay, so what happened? Unpolarized energy vibrates in all possible directions perpendicular to the direction of travel. Therefore, this unpolarized energy makes difficult for radar to identify the energy, and this radar's antenna sends and receives the polarized energy, which is they have the positions such as horizontal and vertical. Okay, the pulse of the microwave radiations is filtered, so its wave properties travel in a single plane perpendicular to the direction of the travel. So what happened? It will filter only from the polarizations that the system permits to receive. It will not receive any other polarizations such as from here and here. It only permits either vertical or horizontal. Therefore, different radar systems have different polarizations system. Some of it able to send and receive only vertical, or could be horizontal, or some of the system able to send the horizontal and receive the vertical, or vice versa. But most of the system will not able to detect both together, right? So here, horizontal energy usually they are quite susceptible, they are able to go for the surface, okay, and the moment it detects, it will go back in the horizontal, and what it will sense, it sense the surface and the surface of the canopy. Okay, while for the vertical, it mostly sense on the top of the canopy or the surface itself, but it doesn't able to detect underneath the canopy as horizontal could be. But okay, so these are the advantage and disadvantage between horizontal and vertical. That's why it's very important to understand why the position is very important. And HH and VV are like polarized radar. Okay, so different positions are exploited in a manner similar to the different wavelengths, and from these different explorations, it able to give you different informations. What are different informations? Okay, I hope that you can detect it, and I will ask you during the discussion later. Okay, so how we basically analyze the radar system? Basically, we look into the surface geometry. So when interpreting radar imagery, you are interpreting the strength of the backscatter and time, right? So what kind of the measurements that we use to determine the radar data, or to analyze the radar data? It is in decibel, which is noise. That's why it has, what we trying to look into are the echoes of the reflected EMR from the object. So strong echoes means near objects will give you bright tones, or weak echoes of far object will brings you dark tones. And the variation in local incident angle also will result in strong echoes of slope facing the sensor, and low or no return slope will facing no return from the slope facing away from the sensor. That's why we can understand, or we can detect the variations of the surface of the terrain by using the radar system like this. So the more the data, the nearer the surface and the bigger the surface, it will give you brighter tones. These are the areas being shadowed or being covered. It will not able to reflect any from radar, so it will show in the blackish color, the dark tones. The more further, it will become darker and darker, and this is how we interpret the radar, okay, visually. So the tendency of steep terrain to hide areas from illumination of the radar beam cause what we call as a radar shadow, and this radar shadow also depends on illumination angle, as shadowing is more severe in the far range portion of the image, like this. Okay, so from here, basically this shows the direction of the radar system, right? So where are the areas being covered? Okay, I hope that you can detect which one, because you need to answer this one in the exercise later. Either this one, are the radar from here, or from here, or from here? That will be the question. Okay, so there are three primary types of radar reflectors. The first one will be the diffuse reflector, okay, the uneven terrain. The specular reflector, usually the flat surface, and the corner reflections when they have obstructions on the surface. And basically, within the different bands as well as the different surface, the incident also will result different tones of color that being collected by the radar. X-band, they are slightly narrower wavelength as opposed to L-band, which is wider. So the narrower the wavelength, the more sensitive the more sensitive the system will be. So it able to show you the surface unevenness on the intermediate surface, as opposed to the L band, which is wider, it still give you a smooth surface. Okay, and for the rough surface, it will reflected what we call it, diffuse reflector, more diffuse reflector shown. However, for the L band, it will show you slightly diffuse, and of course more rougher, then it only can be detected by the L band. Okay, so these are the how it looks like on the surface height variation on these different areas, and how the image looks like. Having a narrow bands, you will see that it able to determine to differentiate between these two, but after that it shows the same roughness. But L band, it able to determine the different the higher the height variation. However, for the lower surface height variation, it unable to, it is not sensitive enough to detect it. That's why by understanding this, you will understand that how the surface will look, how the surface looks like in the real world. And of course, the other thing is we look into the surface electrical characteristics, where the amount of water in the soil, on a rock, or in vegetation increases the dielectric constant of the material. Surfaces with high dielectric constants reflect a lot of radar energy. Okay, and moist soils have high dielectric constant because it has a conductive elements on the soil, and therefore it reflects more radar than dry soils. Therefore, radar can be used to estimate the soil moisture, assuming better range with uniform roughness. Okay, so in soil, basically we use radar to see how soil moisture, how much or the percentage of the soil moisture, and it's also influence how deep radar can penetrate, where water basically reflects radar. Okay, so wet soils only reflect radar in the few centimeters. However, for the dry soils, it can go up to several meters. Okay, so this is the Seine and Nile River. For different kind of the radar bands, it shows how the what you call it, the absorptions and the reflections of the radar. Okay, and radar for the vegetations, it has the ability to provide information of the internal structure of the plant canopies as well as the characteristics of the underlying soil. So what basically it backscatters from the vegetation, it shows you the surface and the volume. So what's good about this? Biomass. Okay, so surface scattering occurs on the top of the canopy and the ground level. Volume scatters occur within the canopy and the ground surface. So what happen? You can see the size of the canopy, and for different kind of radar also it able to determine the density, the volume density, and also the above of the volume and surface and volume scattering from the ground. So what you can get is basically a above ground biomass. So the greater the wavelength, the greater the penetration into the canopy, and short wavelengths tends to affect more by surface scattering, while longer wavelength by volume scattering. So now we look into radar and water. So water is a strong reflector of radar. Basically, it doesn't appear anything because it tends to have a specular reflections. So what is specular reflections? We look back here. Specular reflections. So as the data, as the signals goes to the target, it tends to reflect at the other side. Therefore, the radar will not able to get any reflections. That's why it becomes black. And it's often a setup corner reflection. this. The black one shows specular what we call specular reflections, and it shows in dark color. Now we look into the remote sensing of vegetation. So how basically we use the application and the analysis of the remote sensing for the vegetations. About 70% of the Earth land surface is covered by some type of vegetations, and the characteristic of vegetation is most often recorded by the remote sensing instruments. And as we see that 70% is too big, so remote sensing is the only practical means of mapping and monitoring changes in vegetations over the broad geographic regions on the timely basis. And vegetation-related remote sensing applications include monitoring the agriculture, the forest, rangeland, wetlands, and urban vegetations. And what we see in remote sensing are basically the distribution, the conditions, or the amount of the vegetations. So when we talk about vegetations, basically in remote sensing we talk about the photosynthesis process. Okay, so photosynthesis directly or indirectly sustains almost all life on Earth. Okay, and the plant harness lights, which is EMR from the sun, to produce the energy, which is the glucose, the sugar, raw materials, biomass, and the oxygen. Okay, so basically the photosynthesis takes place in the leaf or other green parts of the plants. And how the process happens: when the sunlight strikes chloroplast, so internal external surface will adapt to perform the photosynthesis, and the plant structures and the interaction with the electromagnetic radiation directly influence on how leaf and plants canopies appear spectrally. And here the interactions happens where the radiant wavelengths, the reflected radiant, the flux of the wavelength, will be combined with the radiant flux of the function of wavelength, and absorb the radiation, produces the incident radiant, goes back to the system of the remote sensing. By understanding the reflectance properties of the individual leaf require understanding of how the pigments of the plant structure, and the water content interacts with the EMR. Now we look into one by one. The chlorophyll. Chlorophyll basically it reflects green radiation. That's why it appears green on the screen. And the structure of the structure of the leaf walls, basically it reflects near infrared radiations. And the water itself inside the leaf that been contained in the structures, the plant water will absorb the energy in the middle infrared, and this EMR transmission is very low for the visible and higher for the near infrared and middle infrared. That's why it makes possible to use the remote sensing to investigate the status of the health of the plant. Okay, you see here, it is most susceptible to be sensed by the near infrared and the middle infrared as opposed to the visible, because it only shows you how green it is. Okay, so when you look into the structure level of the leaf, they are cuticle and the upper epidermis, where the cuticle and epidermal cell layer diffuse and transmit most of the incident lights. And within the palisade layer, they are chloroplasts, which hold the chlorophyll pigments, which is in green. So it will reflect the green color and absorb red and blue. As within the mesophyll surface, mesophyll layer, there contains a lot of water, where it absorbs the water. And here, the structure itself will give you the near infrared elements, and within the water also will reflect the mid infrared, where higher water, more absorptions, So medium infrared reflectors will be mostly absorbed within this layer and significantly shows the pattern of the water absorptions. More water absorptions, more healthy the plant. So what's important points about the medium infrared? Because leaf pigments and structure transmit more of the medium infrared, absorption is almost entirely related to the presence of the water, and also it shows the leaf thickness. Thicker leaf holds more water. Okay, hold more water shows the quality of the plant. Also shows how the functionality of the plant as well, and reflects on the health status. So the spectral characteristic of the leaf changes as it matures or experiences stress. Okay, for example, stress may cause reduction of chlorophyll. Therefore, the color of green will change, become brownish color due to some red and blue being reflected. And changes in the infrared reflectance during the period of stress are also can be identified, such as the degradation of the cell structure or wilting of the leaf. And the increased medium infrared reflectance shows the decreased water content. Therefore, it shows how the leaf become more dry, and it will reflected on the higher reflectance of the medium infrared. Okay, so here within this 0.7 micrometer, change related to reduction of chlorophyll can be observed. Okay, and within this near infrared, the moment the cell wall degrades, it will shows the lower reflectance, and change related to water content become higher reflectance. So because of the variation in leaf pigment concentrations, leaf water content, and leaf structures, the leaves of different vegetations types differs in terms on how they interact with EMR. Even though we just now we talk about the how basically leaf have reflections, healthy and not healthy, different plants also have different properties of the chlorophyll, different pigment concentrations, thickness of the leaf. Therefore, it also shows you different reflectance. That's why very important we know to know that what kind of the plant that we observe, or we are taking the information, as different plants have different properties of the reflectance. Spectral vegetation indices are quantitative measures with the purpose of characterizing vegetation biomass, and they are usually formed through the mathematical combinations to produce single value that characterize vegetation amount of conditions. Okay, so here for vegetation monitoring, so spectral vegetation indices shows better sensitivity than individual spectral bands, where it is sensitive to vegetation covers, less sensitive towards other things, and less affected by the atmospheric effect. And for this one, the normal that we use is the normal. Now we look into the remote sensing of water and aquatic environment. So water basically exists in the various form of on earth, which is fresh water, salt water, rain, and more. Okay, so a significant amount of research has been devoted to develop remote sensing methods such as the water surface area, water constituents surface, ice and snow surface, and many more. It is possible to obtain more accurate in situ measurements of all these hydrologic parameters in very specific locations. However, it's not possible to make enough point observations to create a statistically significant map. So, in remote sensing of water, basically the amount of energy recorded by the sensor explained by the combinations of the downwelling sun and sky radiation that never reaches the water surface, which is the puff radiance, which is the humidity of the water of the atmosphere. The radiation that reach the surface, penetrate about millimeter and reflected, and penetrates within the water and until the bottom. Okay, so these are basically are being reflected, okay, on the water. So the shallower the water, it will able to detect the bottom. Okay, the deeper it will not able to detect the bottom. However, the deepness can be determined through the the, 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 the reflections within the water layer itself. And of course, there are some elements within the atmosphere and the water surface that can give you false data, basically due to the specular reflectance, which give you a mirror kind of water color. Okay, such as here, no sunlight and sunlight, it shows you some kind of the bright, just like a mirror, due to the specular reflectance, and opposed to this one. So the goal of remote sensing is to extract the radius of the interest. Okay, however, most of the time we're only able to trying to calculate the within the water and extract the atmosphere layer itself. Okay, and however, for the pure water, which is free from organic, least amount of absorption and scattering, therefore more water can be seen within the water level, and the color will become bluish, and nearly all incident near infrared and mid infrared is absorbed. It shows you pure water here. So most of the reflectance happen here. But natural water bodies are not pure. They have a lot quantity of the organic and inorganic constituents. So therefore there are some inorganic materials, organic chlorophyll, dissolved organic materials, and also the total amount of the absorption and scattering. Therefore we can and what is the suspended minerals such as silicon and aluminium, and also the soil itself. Okay, and the inorganic is the sediments of the water from the soil. Okay, so what happened requires so basically remote sensing of the suspended minerals requires in situ measurement of suspended minerals. Okay, and of course some near infrared reflected, and the visible range are within the combination of the red and also the green color is often used to provide informations. Okay, so what happened is it shows you the brownish color, as it only shows you the upper side of the water reflectance and not able to give the bottom. Therefore it shows it gives you the idea of how the water is. Okay, and of course in the water there are some chlorophyll from the phytoplankton. So different type of phytoplankton have different concentration of chlorophyll and give you different color. And chlorophyll in water will result some of the strong absorption in the blue and red color. Okay, and a bit of the green peak, and of course there are some of the reflectance peak within the NDVI range. Okay, so what happened is we able to determine algae or plankton within the water here. So therefore we can able to determine the plankton that produce the chlorophyll, or could be the algae suspended on the water, and so on. Now we look into the bathymetry. So basically bathymetry is the idea to survey the water, the bottom of the water. Okay, the optimum wavelength is to obtain the bathymetric information using the 480 nanometer. Okay, if the water is extremely clear, it can go until 10 to 30 meter deep. Okay, so usually due to the remote sensing are not able to give these informations, most bathymetry using the sonar. So for this application, remote sensing is really only useful in very clear and shallow water base, estuaries, river, and more. So usually we are using sonar, and why sonar is basically using the same concept as a radar system. Okay, of course remember that in remote sensing we do have the thermal infrared. So we can use it to determine the water surface temperature. And because water has an emissivity very close to 1, it is possible to obtain accurate water surface temperature measures. And it is only for the surface measurement, and subsurface conditions may be much different. So how when we use this it is meant to monitor the El Nino and La Nina phenomena. So these are the what we call as a sea surface temperature, SST temperature over the area. It shows you the difference of the temperature for the oceans, and thus give you the idea on how the water temperature has been risen over the years. There are some in situ measurement and more. And of course, precipitation can be measured, okay, on a local original basis using the only active microwave sensors such as radar and more. Most area of the world has been covered by weather radar or rain gauge networks, and meteorological satellites also can be used to monitor the precipitation of the areas. So basically, satellite remote sensing measurements of precipitation rely on indirect measurements of the cloud reflectance, cloud top temperature, and the presence of the ice particles in the cloud. Okay, so they are using the visible and infrared techniques, using the visible and the infrared to indicate the cloud thickness, and also using the temperature of the cloud tops using the thermal infrared to estimate the precipitation rate. The colder, the higher the grade, the more likeliness to have the rain and more. And using the active and passive microwave techniques, using the radar to estimate the rainfall of over the oceans and more. Okay, and of course, they are remote sensing also able to monitor or able to capture data of the aerosols and clouds. So understanding the Earth climate system relies on the accurate measurement of three things, which is the distribution of the land surface cover, the amount of type of atmospheric particles, okay, and also the amount, type, and the height of the clouds, right? And these aerosols basically they have a different kind of types and range of the particle size, and typically they tend to have a cooling effect because they tend to reflect sunlight back into the space, reduce the EMR that reach the surface, and the magnitude of the cooling effect depends on the density of the aerosols and the size of the particles. And the cooling effect of the increasing aerosols density may reduce or delay expected warming trends related to increases in atmospheric carbon dioxide. Okay, and a cloud basically play a major role in control the climate because it can warm or cool the surface depending the thicknesses on the height, and different type of clouds height and moisture can be categorized on a single large, limiting the effectiveness of the climate prediction models. So in the visible wavelength, it's quite difficult to show the exact one, only appears white. However, for the thermal infrared wavelengths, clouds are normally cooler than land or water, and it shows you the darker color of the cloud. And other thing is we also able to detect the water vapor, which is essential for the precipitation. Okay, by using the middle infrared, it is possible to detect and to map the distribution of the water vapor. Okay, so water vapor basically being detected at 6,700 nanometer, okay, which is the within the middle infrared, and it interacts within the middle layers of the atmosphere. Okay. And of course, we also enable to show some snows using the remote sensing. Okay. However, it's quite difficult because of the cloud visible portions of the spectrum. So if the image contains both cloud and snow, it is possible to spread them using the middle infrared. where the cloud reflects within the middle infrared. However, the snow will be different. However, by using the active microwave remote sensing, is able to show the snow because of the wavelength wavelength of the radar being used. Can estimate the snow depth, and the clouds will not transparent to the radar system. Now we look into the environment change detections. So the biophysical materials and human-made features are often inventorized using the remote sensing, and after that be turned into the GIS. And some information classes derived are the static and dynamic. Detection of land cover changes provide clues to the nature and rate at which human and physical process work. So these are the general steps used to conduct the change detections using the remote sensing data. We have what kind of the study that you want to do, consideration of the significance of the type of data, using the image processing, and having the results. Success change detection relies on the careful attention to the sensor system and environment characteristics. Okay, so the important one will be the data. The change detection should hold the temporal, spatial, spectral, and radiometric resolution constant. So basically, it is the advice that we use the same satellite and the same environment conditions with the good temporal resolution, so that we can have a very good change detection analysis. Right? So as with the system characteristic, it is desirable to hold environment variable as close to constant as possible. Okay, we try to have environment which is similar to each other in terms of the cloud cover, in terms of the temperature, solar radiations, and more. Why? Because we want to ensure that the data that we analyze will be less affected by those atmospheric effects, as we want to see the changes of the surface. So atmospheric conditions, there should be an absence of cloud or low humidity, but it's quite difficult for us in Malaysia because as we know that we are within the area that is mostly covered by the clouds 24/7, and clouds within that obscure the trends and shadows will cause the problem. Okay, vegetation phenology. What is this? Take an example. If you take the data of the paddy areas, make sure that the next image that you captured is the same area. We don't want to have the first image you captured during the planting, the second image is during the harvesting. Therefore, the difference of color will give a false alarm to the change detection system. Tidal stage as well. Try to ensure that the data that we captured are within the same tidal stage. We don't want to have another data which is during the low tide, another data is a high tide, so it gives you a different ideas of the water volume, as it shows that the boundary of the land has been compromised, so it will give us a false alarm as well. Thank you very much.